So as I was telling that oftentimes the dynamic programming problems are like examples of optimization problems. So what is an optimization problem? Typically, a problem instance here will have many candidate solutions. Okay, each solution will have some sort of a value associated with it. The final solution to the instance is the optimal value. Now this optimal value depends on the problem statement. It could be the maximum, it could be the minimum. Okay, depends on the problem statement. Now, if we try to think of finding the shortest path, as an optimization problem, so what will be the clauses here? Candidate solutions. What are the candidate solutions? What are the candidate solutions here?
Sir, all paths from
All paths.
Yes.
All paths between a pair of vertices. What is the value?
Sir, sum of weights of each.
That is the path length, right? The path length. And then what is the solution? Optimal solution?
Minimum of path with smallest length.
Path with smallest or minimum value, which in this case is the path length. You will see that whenever, even when you have graduated, you will see that there are many instances, real world problem instances, where you will encounter optimization problems. And in many such optimization problems, DP is kind of a very handy framework. Okay, that's why DP is like, as I was telling you, that's why DP was very much in use in the control theory, where they had lot of applications of DP in doing optimization. Okay, so now with this primer, we will start off with the design of the shortest path algorithm. We will take a working example where we have a graph which is both directed as well as weighted, which is the most realistic like simulation of a, say, connectivity between cities. So you might all like to draw, if you have a like torn paper or a note page, then you might all like to draw this, because multiple times I'll be referring to this figure. Okay, I'll try to come back, scroll up and come back, but it might be a handy thing to do it yourself so that you can cross verify. Okay. So now, as I was telling you last day, did you try to see like what is the brute force? What is the brute force leading you to? So the brute force is to find the paths that are present between any pair of vertices, and from there choose the shortest one. Okay, so this would be a brute force uh, algorithm. Let us make it a little bit more specific. By this you mean all. You want to find all the paths that are present between any pair of vertices, and from these set you want to find out the shortest one. Now this obviously has caveats, and yesterday I already uh, requested you to try this homework. So today we will see like what is the issue with this. So let us say that you have a complete graph with weights. So there are weights on the edges. Okay. So what is the total number of paths possible between a pair of vertices?
N minus 1. No, sir. Like it is a factorial means n minus 1
And
factorial.
how do you arrive at that?
Sir, we try to find a summation of all the paths. Means we try to see where means different choices. We can include different nodes in the path, and the order in which I will choose the node, that also can be varied. So they will contribute to the overall answer.
So when you are asked this kind of a question, it is best to answer it using some sort of a hypothetical picture. Your answer is absolutely correct, but for the ease of your friends, I am trying to construct the example that you are suggesting.
Sir, edge between V1 and V3.
Yes, I have not finished.
Sorry, sir.
Tell me if there is anything else left in this graph. Is there anything else?
Sir, are we
No.
considering directed graphs or undirected graphs?
For the time being, let's say undirected. Directed also works. Okay. For the
Okay.
time being, let's say undirected but weighted.
Okay.
Okay. Let's say something like this. Now say you want to enumerate the paths, all the paths between V1 and V4. What are the possibilities? Say V1, you start with V1. Now in the next line of choice of vertices, how many choices are possible?
3.
3,
Oh,
right? Then
2. 2 and then 1.
2 and then 1. Now try to generalize this for n vertices.
Yes,
Say
sir.
now I
N
have,
minus 2 factorial.
yeah. So basically then here n minus 2, then n minus 1 up until 1, right? So then
I think why cannot I draw an edge directly from V1 to V4?
why cannot you draw? Tell me, you tell me. Why is so I have asked you all paths.
Yes, so that is also a path.
Okay, fine. Agreed.
Yes, sir. Plus 1 should be there, I think.
Fine,
Yes.
fine. Take it. Take it. We are interested in the order. We are interested just in the order.
Sir, I didn't get how you are counting this 3, 2, 1. Can you explain that?
So from V1 to V4, okay?
Yes, sir.
So you can go via V2,
Yes, sir.
you can go via V3,
Yes, sir.
and you can go via V5. So 3 possibilities. Okay. Now say you have chosen the second vertex. Say you have chosen the fixed the chosen vertex to V2, right? Now then you can go via V1, V2, then V3, then V4, or V1, V2, V5, and V4. So at the second step, there are 2 choices. In the first step, there were 3 choices, V1, V2, V3, V5, right?
Sir, why are we not considering the direct? I mean,
Okay, you consider the direct one. You consider also the direct one. That's also a path. The single edge is also a path. Okay. The single edge is also a path. You can add that. So I am interested in all paths. Okay.
so shall we consider the paths as with 3 edges, with 2 edges, with 1 edge?
Yes, yes, all paths. You have to
Yes.
enumerate all paths.
And
Okay.
for a path with 3 edges will have different paths like a V1, V2, V3.
Exactly, exactly. It will have V1, V2, V3.
V.
Sorry, it will have if it is 3 edges, then it will have V1, V2, V3, V4, or it can have V1, V2, V5, V4. Right. So we say V2 is you have anchored on V2. Then you have 2 choices. Okay. Similarly, you can anchor on V3. Then also you will have 2 choices. You can anchor on V5. Then also you will have 2 choices. So with 3 edges, you have how many choices? How
Two
many
choice,
paths possible?
2.
2. In this way, if you generalize for n cases, what will be the situation? Let us assume that the single edge is trivial. Okay, single edge is trivial. That is always there. We can add that one path at the end. But otherwise, how many paths are possible if there are n nodes?
Sir, n
So,
minus 1 factorial.
yeah, so in this stage, you have n minus 2 choices. In the next stage, you have n minus 3 choices.
Sir, we can add
Next,
one to all of them because we can have a choice of not choosing any of the.
yes, you can. Agreed.
Sir, then it will start from n minus 1, then n minus 2.
True. Agreed. So the one case is, I am assuming that it's trivial. That's why last day I said n minus 1. Okay. So the one case is trivial. So that is, so let's not try to be very specific, because finally what we are interested in is the order. So it's order n minus 2 factorial, which is order n factorial. Okay. So these many paths you will have to compute.
Sir, order n factorial and order n minus 2 factorial are different, right? Because it is n square times n minus 2 factorial.
I don't understand why they are different.
Sir, n minus 2 factorial multiplied by n minus 1 and n will give us n factorial. So how can they both be equal?
Order,
Sir, n minus 2 factorial, n factorial is n minus 2 factorial into n minus 1 into n, right?
yes.
So how can the both orders be same?
It's
Order
not
of,
same. It's not same. What is the definition of order?
okay, sir.
So,
Yes,
but n
sir.
factorial is n
Order,
square times more than
order,
n minus 2
order n is
factorial.
not in order n square.
Yes, sir, it is there. Okay, sir.
See, if you start mixing up things, then it will be difficult for you. Okay. Remember, you have to remember the basic premises. Okay, so fine. So now this is, what can you comment about this? How bad is this? How bad is this?
Sir, n to the power n, like yes, you can
So
say.
worse than exponential, right?
Yes.
What kind of information?
Yes, sir.
So therefore, it's a very bad algorithm. If we want to do it in this way, okay, I am again telling you that here in each of these, you can just add one more because of the direct edge possible. Okay, so, but we are not interested, as I say, the single edge case is, let's say case, the single edge case is trivial because finally what we are interested in is in the order of computation. Okay, so now we want to do better. Okay, so for this, as we said, Floyd has an algorithm for us. Let us say is the weighted adjacency matrix. So then refer to the previous figure, the graph that I have drawn. This is the weighted adjacency matrix. Okay. Now I define something in addition, which will help me to.
Can you scroll a bit up? Like that condition ones. Yes.
Done.
Done, sir.
Okay. So I define an additional matrix D. Okay. And how is D defined? D is defined as follows. Dkij is the length of the shortest path from Vi to Vj using only vertices in the set V1, V2 up until Vk as intermediate vertices. Okay. So note the definition again carefully. We will see an example. Things will get clear. Length of the shortest path from Vi to Vj using only vertices in the set V1 up to Vk, okay, as the intermediate vertices. So no other intermediate vertices are allowed other than V1 to Vk. That is the condition. Now let's say we try to obtain some of the D's for our graph. This is directly length of and in this case this is how much?
So directed length of V2 V5 or V1 V5?
Sorry, V2 V5. How much is this? With no intermediate vertices. That is the direct edge.
Infinite, sir.
Huh?
Sir, infinite.
Infinity. Yeah. So there is no directed edge between them. So therefore, the edge length is, or this entry in D1, sorry, in D025 is infinity. Now D1. So this is minimum of length of V2 V5 and length of V2 V1 V5. As you have been told that only intermediate vertex V1 is allowed. Okay. In this construction, only the intermediate vertex V1 is allowed. Okay. So this is minimum of infinity. And how much is V2, V1, V5? Can you please quickly calculate and tell me?
Sir, 14, sir.
14. So this is 14. Okay. Now you keep on doing this. D2 to 5. Okay. Now can you tell me what is D2 to 5?
14 only.
14 only. This is equal to D1 to 5. Why? Because for any graph, shortest path starting at V2 cannot again cross V2, right? So therefore, D25 is exactly equal to D15. Sorry, D225 is exactly equal to D125. Now D325. How much is this?
Sir, I think it is 10.
10.
No, sir, not 10, sir.
Calculate carefully. Tell me. I'm hearing.
V3 to V5 there is no direct touch. So
Yes. So V3 does not introduce any new path, right? Inclusion of V3 does not introduce any new path. So therefore, this is now next. D4. How much is this?
5.
Minimum of length of V2, V1, V5, length of V2, V4, V5, length of V2, V1, V4, V5, length of V2, V3, V4, V5. So that is minimum of, this one we have already calculated, 14. This one would be how much?
Sir, 5, sir.
5.
5.
Next one will be 13. Next one will be 10. And so this one is 5. How much is this?
Same as D4 to 5.
D425. Because shortest path, again the same reason. So the shortest path between V2 and V5 is 5 because K's max value has been reached. So in this way, you can compute the shortest path between any pair of vertices through the set of intermediate vertices that you keep on changing. Now, how do you build up this matrix D? So this is where comes the idea of the optimal substructure. Okay, so D n ij is the length of the, as we just now saw, length of the shortest path from Vi to Vj. Okay, and D0j, D0ij is what?
Sir, Wij.
Wij. So therefore, we start from D0 equals W, and we have to reach Dn, which is equal to the final shortest path matrix. Okay, shortest path length matrix. Now, my task is, given these two, my task now is to establish a recursive property which will help me to compute what from what? What am I targeting to compute? Dn, right?
From D0.
So what from what? What will be the recursive property on? What is the
Dn.
recursion on?
Dn.
Huh? Dn?
Dn
I should be able to compute dk from, I should be able to compute somehow compute dk from dk minus 1. And then my question is, what are the different possible ways to compute dk from dk minus 1? Now, if I can solve the instances, then I'm done. Okay. If I can solve the instances one after the other, then I am done. Now, in order to establish this recursion, we have to carefully note that there are two cases that are possible. So the first case is that at least one of the shortest paths from Vi to Vj using only vertices in up to Vk as intermediate as intermediate vertex does not have Vk in it. Okay, does not have Vk in it. So then in this case, what can I write? Dkij should be equal to
dk minus 1 ij.
very good dk minus 1 ij. Can you reiterate some example of this form that I showed you just now in the previous enumeration? Can you remind me?
Sir, D3.
D3. D3 of 2, 5, right?
Yes, sir.
D3 of 2, 5 was D2 of 2, 5. This was one example. Now the case 2 is interesting, is more interesting. So the case 2 is the opposite, where all shortest paths from V1 to Vj using only vertices up to Vk as intermediate uses Vk in it. In such a case, how will be the situation? If you think of it pictorially, there is Vi, there is Vk, and there is Vj. Okay.
Sir, we can say path from I to K and then path from K to J.
Excellent, excellent. Yes, that's what we are going to do. Very good. So we are trying to compute a shortest path from Vi to Vj, okay, using only Vk as intermediate. Fine. Now, out of this, what is this? What is the first one?
Vi.
Our shortest path from Vi to Vk,
dk.
right? Using only vertices and another shortest path from Vk to Vj using only vertices So what is the length of this subpath?
dk of I comma k.
dk.
Sir, k minus 1 also, because
Yes,
right,
dk minus 1 I comma k. Because vk cannot be included in this path anyway, right? vk cannot be intermediate. Although we are telling v1
Yes,
to
sir.
vk
Yes, sir. Yes.
by construction, but vk cannot be an intermediate.
Yes, sir.
Similarly here. So this one is
dk minus 1 of k comma j.
K comma J.
k comma j. Right? Now, any path cannot be shorter than this. Do you agree with me? This is by construction, because you have said that dk minus 1 is the shortest. Right? So if there was some shorter path, then we could have constructed it already using v1 to vk as the intermediate vertices. But you have said that dk minus 1 ik is the shortest path. So there cannot be anything shorter. Similarly from the other side. Okay. Fine. So then these are the, so now do you see where the story of optimal substructure comes in? Small tidbits make up the whole. Right? So here you can write for this case 2, therefore you can write dkij is equal to dk minus 1 ik plus dk minus 1 kj. Okay. For instance, if we need to compute d2 5 3, then we can do it by computing d1 5 2 plus d1 2 3, and you can verify this yourself. This will be 4 plus 3, that is 7. So then what would be my overall recurrence? Considering both case 1 and case 2, what would be my expression for dkij?
So minimum of case 1 and
Very
case
good. Minimum of case 1 and case 2. dk minus 1 ij, comma dk minus 1 ik plus dk minus 1 kj. Okay. So this is how you compute the next value of the D matrix. The next iterative value of the D matrix. Now, once we have written this recursive algorithm, do you think, sorry, recursive formulation, do you think is there any difficulty to write the pseudocode? We are done, right? So this is the most interesting and intriguing part of any dynamic programming algorithm. The hardest part is to establish this optimal substructure, and from there the recursion. Okay, once you are done with the recursion, it is very easy to write the pseudocode. So for instance, suppose you want to find out D2 5 4. Okay, so then this will be minimum of D1 5 4 comma D1 52 plus D1 24,
Sir,
right?
sir, here in case 1, we are assuming that there must be at least one path, right? There need
Yes,
not.
of course. Of course, there is at least one path that does not cross VK. I mean, that does not use VK. So this can be further written as and in this way you can unfold and finally find out the value of D254. Now, one of you asked me yesterday, I don't know whether you are present today, one of you asked me yesterday that why this is a bottom-up approach. Now, do you see how the table is getting filled up in the recursion?
Yes, sir.
Small to big, right?
Yes, sir.
You
All
have to
the
find,
myths starting from 0.
yeah, you have to pre-compute the zeros first, then ones, then twos. Although, because of our familiarity, we are going down like as if we are unfolding a recursion, but we are filling up the table upward, right? That's why the bottom-up notion.
Sir, but even in divide and conquer, we divide from top to bottom and solve from bottom to top.
Yes, but the approach is bottom to top. Sorry, approach is top to bottom. You break it. Here you don't break anything. This is just an abstraction to show you. You don't break anything. You start computing from here. You first compute D054. In divide and conquer, you have to break. Unless you break, you cannot solve it. Here you don't need to break. You have to start solving from D0. Your table has to be filled up from D0. Agreed or not?
Sir, for calculating dk, we broke it into dk minus 1, no, sir?
We did not break it. This is a way to show you. This is an abstraction. Internally, no breaking is going on. Is there any breaking going on? Think of the pseudocode.
Yes,
In
sir.
divide
Yes,
and
sir. We are
in the
calculating n minus 1.
exactly. So in the like divide and conquer, you have to break it using recursion. First, you have to break the array. Here, there is no
Yes,
such
sir.
breaking happening. Think of the pseudocode from this. This is an abstractive way of showing things so that it's easier for us to understand. But actually, internally, what is going on? You are building the matrix from the bottom, right? In divide and conquer, unless you break the array into sub-arrays, you cannot solve it. So think from the pseudocode or the coding perspective.
So here we need to first solve the unit element like D zeros to find the final answer.
Exactly. You see,
And,
I'll write the code and this will be clear.
and sir, in the divide and conquer, if we don't solve the base case, we cannot find the final answer.
Yes, but you have to break the array. Here you don't have to break anything. There you have to break the array. For doing merge sort, you have to break the array first. Okay. If you
Yes.
have to do merge sort, you have to break the array first. Here you are not breaking anything. You are starting from the bottom. You can very easily start from the bottom. That's what you will see in this algorithm when I write the pseudocode. I'm not writing the pre-steps, like there is the problem statement, the inputs, etc. You can, the input here is W and N. Output is what? D.
So sir, here, irrespective of what we did till now, we will first compute the initial values like D0.
See what I'm doing. See, you'll get to understand.
Sir,
Yes.
to implement this algorithm, I mean, does D have to be a 2D matrix, or I mean a 3D matrix, or a 2D matrix will also do?
Why 3D? 2D.
I mean, like we have to calculate D0, D1, D2. So I'm thinking like we have to build a 3D matrix for that.
No. I'll show you how to do it. The same Dij can be updated.
Okay.
Do you get me? You can forget the previous one. The same Dij gets updated.
Achha.
See, so much of toiling for such a simple code. Done.
Sir, sir, di comma j is equal to minimum of di comma j.
Yes. Yes. Previous Di comma j. This is a variable where you are storing things. The previous value of Di comma j and Dik plus Dkj. That gets into the new Dij. C variable. This was something,
Yes, sir.
was getting stored here.
Yes, sir.
Can you not write A is equal to minimum of A and B?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Means it was value is of k minus 1 loop and now loop is new.
Exactly. So K
So
minus
it
1
would be
was being
k.
stored here. K minus 1 was being
Yes, sir.
stored here. Now it will become K. So you don't need additional that K variable. That 3D part is gone. One
Yes,
of you
sir.
were asking. See, so much drama for such a simple code. So the moment you are able to write the recursion, DP becomes very easy. Coding of DP is very, very easy. And now do you see why is it bottom up? You start with 1, 1. You start building with 1, 1. This you cannot do in divide and conquer.
Yes.
Now, is it done? Is the problem solved? Or something is left? What
So
have we come?
the answer is left.
Bolo? No, so the shortest path matrix is created. But we have one more task left. What is that?
Finding the minimum value.
Yeah, no, value is done. Minimum value is done. So here, like every cell will contain, in D, every cell will contain what?
Shortest path from I to J.
What is the minimum? What is the shortest path length between those pair of vertices?
Yes.
So for the example graph that we took, okay, so you take up any pair of vertices, any pair of vertices, and look at the corresponding cell. That is the shortest path length between those pair of vertices. So that is why this is also the all pair shortest path. Given this matrix, this path matrix, you can immediately identify all the shortest paths, okay, path lengths. Now what is left? I have already given you the hint. To output one of these paths that is left, right? We have to output one of the paths. We have just given the distances between pairs of vertices, but we have to compute or give a pseudocode to compute the path between any pair of. So there might be multiple such paths, shortest paths between a pair of vertices. It suffices to print any one of them. We have to print any one of these vertices, sorry, any one of these paths. Say between V1 and V5, there might be multiple shortest paths. You have to print one of these. How do you do it? Okay, so this we will solve next week in the Wednesday class. Okay, so this does not have a DP formulation, so the DP formulation is over. So getting the distance value, shortest distance value between any pair of vertices is where the DP is required. So the DP formulation is done. We have got the distances. Now in the next class, we will solve the exact path finding. We will find out the path, any one of the shortest paths between a pair of vertices. Okay, and then we will also do the sequence alignment problem that I have promised. Vishal, are you here?
Yeah. Yes, sir.
Yeah.
I'm here.
So yeah, over to you.
Sir,
Okay.
Yes.
so with this matrix, we can find shortest path between any two vertices, right? Not only the required one.
That's what I said, all pair shortest path. Any
Yes.
two vertices. That's why all pair. This matrix is a very good matrix that way. Take up any pair of vertices and you want to know the shortest distance between them. You call this, I mean, you look at that cell, you invoke that cell and you get the value. As simple as that.
So directly Vij, I mean here Wij will give that shortest path.
Dij, not
Yes,
W.
yes,
Dij. Dij, the final Dij will give you the shortest path. Okay, over to Vishal.
Sure,
I'll
sir.
stop sharing my
Yeah.
screen now.
Sir, yeah, I also need the permission to
Yeah,
share.
I'll permit you. Just a second. Give me a second. I'll just stop sharing. You should be able to present now.
Yes, sir. I'll try. Okay.
Are you able to present?
Yes, sir. Yeah.
Okay.
So is the screen coming up?
Yes, it has come up. Yep.
So yeah, hi everyone. So I will be sharing two examples of dynamic programming based problems and one solution, one C++ code solution using dynamic programming. Okay. So the first problem is longest common subsequence finding between two input strings. So the basic routine that we usually follow, like Sarah has also discussed, first you have to identify a recursive formulation for the solution and need to find out whether the optimal substructure property holds for that solution, and then see whether there are repeated subproblems that will lead you to have a dynamic programming based solution. Okay, so we'll try to do that in these two problems today. And the two general approach that you can follow is one is memoization, another one is tabulation. So memoization is usually more similar to the recursive call that you are writing the recursive formulation, and you can go top down. And the only thing you are doing is whenever you are making a call, you are saving all the solutions that you are getting from those calls. So when you have overlapping sub problems, you can basically remember those calls that you have made earlier and just take the solutions from there. Whereas in tabulation, what you do is you create the solution from the bottom up, just like you saw in Floyd version. So you basically start with the base case 0, 0 or 1, 0, and you start building up the solution for the larger problems. So now to the LCS problem. So here the question is like this. You have two input strings, A and B. And what you have to identify is the longest common subsequence between these two strings. Now subsequence means here that given this input string, a subsequence can be any set of letters, but in the same order as they appear in the sequence. So the order must not change, but they doesn't have to be consecutive. So like ACT is these first three letters, that is one subsequence, but ATTC, which is not like consecutive, these letters, is also another subsequence. Okay, and now so the longest common subsequence is basically if you have two inputs A and B, which are both strings, and you saw the definition of the subsequence, then you have to find out the common subsequence between these two strings, and it needs to be of maximum length. Okay, so suppose you have these two inputs A, B, C, D, G, H, and A, E, D, F, H, R. So A, D, H, this subsequence appears in both the input strings. Okay, so and this is also maximum length. You cannot find anything else which is longer than this. So that's why this is one LCS for these two input strings. So we need to find out an algorithm. We need to devise an algorithm to get this longest common subsequence for two inputs. Okay, so now if you think about the brute force solution, so that you can enumerate all the subsequences of A and check if that subsequence also appear in B. Now, as you can see, like enumerating all subsequences of A is a very highly complex solution, and it will have a combinatorial complexity. So that will take a lot of time, but the matching can be simple, but this first step is very complex. So even if you implement this, it will, for very long sequence, you will not be able to run this code. So that's why we need to look into some other solution. So first, to construct the recursive solution, we need to look at the optimal substructure property that can hold between the input sequences X and Y and one of the LCS Z. So the first property that you can notice is if you have been given a longest common subsequence Z, which is of length K, and you have the inputs of length M and N, then this longest common subsequence Z will have the, okay, so the first case is that for the input sequences, if you have this final letter, same, so xm is equal to yn, then the last letter of this LCS will be the same as this. Because if you exclude that, so you will only get a smaller subsequence. So you need to consider this last letter. And that happens if the final letters are same for the input sequences. Now, the second case is that if the final letters are not same for X and Y, then the LCS can be this. So it can be between xm minus 1 and y. So xm minus 1 is you take x from x1 till xm minus 1, excluding the final character of x, and y is the full sequence. So this can be this, or if again the third solution is also the same condition, the xm is not equals n, then the LCS can be the LCS of x and y n minus 1. So you basically need to look at these two cases and find out the longest of these two. And if they're same, then the first condition holds. Okay, so based on this, we can formulate the recursive solution, which looks like this. So Cij is basically telling you what is the length of the LCS for your input sequence A and B. Okay, or let's say X and Y, which are of length M and N. Okay, so Cij is basically saying what is the length of LCS if you consider the first sequence up to length I and the second sequence up to length J. Okay, so that is given by, so if the final letters are same, so Xi is equals Yj, then you can get the solution from the I minus 1 and J minus 1 prefixes of X and Y and add 1 to it, because the final one will be included. And the second part is if they are not equal. So this is condition 2 and 3 that we saw earlier. So this will be a maximum of, you get the solution from Xi and Yj minus 1. So you are excluding the final letter of Y, or you take Xi minus 1 Yj, you exclude the final letter of X. Okay, so the solution would be either of these three. If the first case holds, it will be like that, and if the second case holds, then it will be maximum length of either of these two cases. Okay, and so yeah, so this is the recursive formulation. So can anyone tell me like what would be the base case for this solution? So this is for I and J. What would be the base cases?
1, 1.
1,1.
You were saying 1, 1, but there can be
This
other
case
theories
can
also.
be like if one of the length is 0, then the other one, then we just return 0.
Right, exactly. So if either of them are 0, so this will be 0. Okay. So basically, if one of the string is 0, so there cannot be LCS. And based on these two solutions, these two base cases, you can find out the solution. Okay, so that is just shown here. Now, to look at the overlapping subproblems, so we found out this recursive solution for this. Now we need to confirm that there are overlapping subproblems so that we can apply DP. So let's consider these two input sequences again, ABCDH and AEDFHR. So these are of length 6, right? So when you try to write down C6, 6, so this is the final cell. In the recursive call, it will give either C5, 5 plus 1 if X6 and Y6 are equal. And if that is not the case, it will be max of C65 or C56. So this is basically if this cell on the right is 6, 6. So this is trying to look at this cell on the top, or the corner cell behind it, and or the leftward cell. Right. So this particular cell is asking for these three cells. Now, if you look at this this cell here, so this is also asking for this particular cell on the top. Right. So you can see that this cell is being asked. The solution for that cell is being asked for repeatedly. And the same happens with these other cells also. They will also get called repeatedly by some other cell. Right, so we have this overlapping subproblem scenario also. So we can now try to code it up as a DP problem. Right? So this is the final pseudocode. So we have this X and Y as inputs, and we have to find out the lengths. And so we'll start with getting the lengths of X and Y, and you initialize the C matrix that we need. Right. So we saw that if any of the inputs to C is 0, then the solution is 0. So we get the first rows and the first columns of the C matrix. Then you start from the bottom, right? So I equals to 1 to M and J equals to 1 to N. So if Xi equals to Xj, then you simply have you take the value from Ci minus 1, J minus 1 plus 1. And if that is not the case, so this is the else case for that. So you have to see if which one is bigger. So Ci minus 1, J or Cij minus 1. So these are the corners that you saw earlier. So either maximum of this or this. Right? So if you just run this loop, then your C matrix will get filled up, and the final cell, the bottommost cell, like the right bottom corner, that will contain the solution for your current problem. So yeah, so can you tell me like whether this is tabulation or memoization, this particular solution?
Sir, I think it is tabulation.
Right, so because we are going from bottom up, and so I explained the matrix C here. So can you see there is also another matrix called B that is being filled up here and here and here. So can you tell me what is the use of that matrix?
So yes, it will show the directions from where we have to go from 0, 0 to n, n.
Right. So this will tell us like
we can
actually
actually write out the LCS.
yeah, so exactly. So we need this B matrix to write down the LCS. So C matrix only will give you the length of the LCS, right? But we also need the solution or like the actual LCS. So for that we need the B matrix. And we do not, so for finding this LCS, we will not start from the 0, 0 corner, but instead we will start from the bottom corner. Okay, because you have the LCS final cell, the length of the cell here. So we'll start from here. So this will probably give a direction, let's say like this. So if this is the direction, you include this letter and then you go to this cell. Okay, then you include this particular letter and again you'll go here. So if the direction is given like this, so you will start from here and try to follow these arrows till you reach this first 0, 0 cell. Okay, so this is basically the B matrix, and based on this you can get the final LCS sequence. Okay.
Sir, I didn't get how you are getting the sequence with the arrows in B.
Okay. So if you see how they are filled up, so if this in this first case, you have xi equal to yj, right? So they are both same. So then what you are doing? So suppose this is that cell where xi equal to yj. Now here we are filling a corner arrow, right? So this is telling that from particular cell, if you are to include this xi or yj as your solution, then you need to, the previous letter would be from here. So that is yj minus 1 and xi minus 1. So this is what that is telling. Okay, so to solve this problem from here, you need to reach the corner, the cell that is on the top left corner of that cell. Okay, and if you see this particular cell, so this is saying that your xi and yj are not equal. So that's why this particular arrow is coming. You cannot include this particular letter, but instead you should go up. So we are basically here, we are excluding this letter from the solution. This xi is excluded, and that's why this up arrow is showing. So up arrow is telling go up to this particular cell here, and you can get the solution from there. Okay, so if you follow this, you will eventually reach this 0, 0 cell, and you will basically have a solution at hand.
And also, sir, the Cij matrix shouldn't we run like for I 1 to m and for j 1 to n and all Cij equal to 0? Why are you running it like that? Only the first top row and first column.
Okay, you mean these two, right?
Yes, sir.
Yeah. So if you remember, we had the base case here, right? This is the recursive solution. If xi equals yj, then we can include that later and just add 1 to the previous solution, right? And if the other case is there that they are not equal, then we can try to look at what is the maximum of the previous solution. We exclude xi or yj and see what is the solution. So this is the recursive form. But we need to start from somewhere, right? So this will just tell you like what if you have the previous solution, you can find the next solution. But we need a starting point so that we can get the next solution, right? So that is this 0, 0 case. So this 0, 0 case is saying if you have this C matrix, and this is like sorry, 1 second. This is your sequence y1, y2 up to yn, and x1, x2 up to xn, right? So if you consider length 0, okay, actually we need to include y0 also. 1 second. Yeah, so if your sequences are like y0, y1, y2 up to yn, and this is x0, x1 up to xn. Now this x0 is basically saying that you are not including anything from x, it's just an empty string, and y0 is saying it is an empty y string. So in both of these cases, these answers will be 0 because in the first row your x string is empty, and in the first column your y sequence is empty, right? So you cannot have any LCS because one of the sequence is empty. Right? You got that part?
Yes, sir.
Yeah, so that's why we are initializing these arrays here. So for I equals 1 to m, we are filling up the first column here, ki C I comma 0 is 0. And for j equals 0 to n, we see 0 comma j. So this is the first row being filled up with zeros. Okay.
So then what is the purpose of it? If we don't use them, we can directly run from...
Oh, no, we do use them, right? So when you are trying to solve, say, this particular point, ki j equals 1 to n, I equals 1 to m. So this will try to call for C0 comma something or C something comma 0. Right. So these particular entries, this will try to retrieve those 0 indices also. So we need those base cases.
Okay.
Okay. So yeah, this is a very important part. So whenever you are trying to implement a DP solution, you need to take good care of the base cases. If you don't have the base cases, your code might give seg fault or something. Okay, because you don't
Sir,
have anything defined there. Yeah.
sir, we haven't even initialized the bi comma j to 0, right, sir? Means
Right. Mhm.
except these arrows, we are not defining, means we are not initializing anything.
Exactly. So
Okay,
can
sir.
you tell me why? Like any idea?
Sir, because means we just want to know the part and rest of the things we means don't want to know. That's why, sir. Yes.
No. So the reason is that so you are solving the problem using the C matrix. Okay, so B is not actually your DP solution. The C, how you are calculating C, that is the DP solution. B is only telling you how you calculated that solution. So B is remembering the steps you used to calculate the C matrix. Right. So you don't really need the base cases for B because you have the C matrix.
So, but how to obtain the like after returning B, how to obtain the direction from B?
Okay, I'll explain that part again. So you have 3 types of arrows, right? So one is this corner arrow, then you have the upward arrow and the leftward arrows, right? So what does the corner arrow say? Corner arrow says ki your xi and yj are equal. So we include them, right? So if you see a corner arrow, include xi or yj, they are equal. Okay. If you see a up arrow, so that is this particular case, it is saying that xi, so both of these cases are xi and yj are not equal, right? So we cannot include them. So this up arrow is saying ignore xi and move up. Okay, so it is saying since they're not equal, let's look at the solution at the top. And the left is saying ignore yj. So it is basically shortening one of the sequences. And if you see the this corner arrow, that is basically saying we have found a match and this goes to the solution. Right.
So, sir, after we got the final B matrix, where there are corner arrows, those are the characters which we want for the sequence.
Exactly. So at those points, xi and yj are equal.
Sir,
Yeah.
after we form the B matrix to actually write down the LCS, do we go from top left to right bottom or from right bottom to top left? I mean, which direction should we go?
Right. That's a very good question, actually. So while implementing this, you will have to take 2 steps. So the first step will be you have to start from the bottom corner, because you can only backtrack from the bottom corner because that is the final solution. Right. So if you start from the top left corner, you will not know which path to follow. There will be several paths. Right. So that's why you start from the bottom corner. But when you do that, you will get the LCS in reverse order. So after you have found the LCS, you have to reverse it once because you got it from the end. Okay.
So, sir, LCS will contain that characters which have corner arrows.
Right. Yeah. So it will not be like not all the corner arrows because there will be multiple cases. So you are looping. You are doing an n square loop, right? So there will be several spaces where can have a corner wherever xi and yj are equal. But we will only consider some path within this matrix, something like this, of which we will take the corner arrows that appear on that path. Okay, and that will be given by this backtracking that I'm talking about. You start from this corner cell, the right bottom corner cell, and you start backtracking.
Sir, is it necessary all corner arrows will appear together, or they may appear it's like in between we can have the arrows which are pointing to the top and also to the left?
Yeah, you will have top and left arrows also, right? Because the sequences are different and maybe of different length. So at some point, the B matrix will tell you to ignore certain characters in sequence X or sequence Y. So in those points, you will see up arrow and left arrow. And wherever it is finding a match that needs to be part of the LCS, there you will see the corner arrow. Okay, so basically it will be like you start from the bottom corner. Let's say you saw up arrow. So you go to this cell. 1 second. Yeah. Let's say you saw up arrow here. You will go to this cell. And there, let's say you got a left arrow. So they will go to this cell. Then again, say you got two up arrows. So you will go up and up. Now here you got the first corner arrow, right? So you will include either this X or Y. And these will be same, right? Xi and Yj because there is a corner arrow. So this is the first character you got for LCS here. Now after that, let's say you got again a left corner arrow. So you again include this. And then after those first two characters, you were getting all left arrows till this first cell. So basically your LCS will be only those two characters where in the path you got two corner arrows, and rest of the things wherever it was left or top, those are just directions. You are not including.
Sir, so that means we cannot have something like two corner arrows, then two arrows which are pointing to the top, then again two corner arrows. Like that is not possible, sir. Because all the characters should be coming all at once. Means, like if Yj means if the sequence contains Yj and Xj, and if it also contains like means not Xj but like Xi, so then if it has to contain something else, it can contain Yj minus 1 and Xi minus 1.
Right,
Because,
yeah.
because we will go one back within both of them because it has to be consecutive. So all the corner arrows should appear together. If they have
No, that doesn't have to be the case, right? So the solution can be right. You just match the final character and the first character. Okay, let's say that is the case. So that would look like you have a corner arrow at the right bottom, and then after that it might be all, let's say, up, and then finally a corner arrow somewhere. So there would be two corner arrows only, and they will be far apart.
Okay, sir.
It can be anything, or you can even go like this, like up, 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 then left, 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 and then a corner arrow. It can be like that also. Okay. So we'll move to the second question now. So this is the previous year DP lab assignment. So you can actually go through the question, or I can like explain. I can try to explain. So basically the question is something like this. You have n reactions. Okay. So basically you are given n reactions, which are numbered 1 to n. And the first constraint is that all of these must be completed for successful completion of the system, of this like set of n reaction system. And the second input is you have C catalysts, and each reaction need at least 1 unit of catalyst to even start. Okay, so this is another constraint. Now the final, so you are given another matrix EKP, which is a n cross C matrix. So this is saying the probability of success of reaction K if P units of catalysts are used. So like if you consider EK comma 0, so this is like reaction K with 0 catalyst. So that will be 0 because without the catalyst you cannot run the reaction. Now if it is EK comma, is there any question?
Yes, sir. Sir, P units of catalyst means P different catalysts or P units of a single catalyst.
So you only have one catalyst. So one catalyst of
Achha,
C
okay.
units. Okay, and there are n
Okay, sir.
reactions, n different reactions. And EK0 is basically saying without any catalyst, the probability of the reaction happening is 0. So you cannot run the reaction. Now the following probabilities where EKP is there and P is greater than 0, so P is a positive value, those values will be something less than 1 as probability of that reaction K happening with catalyst amount P. That is given as in that is given in the E matrix. And also another constant is given that this E matrix is non-decreasing with respect to P. Okay, so if you increase the catalyst, the reaction probability will not decrease, it will always increase, or like it can remain constant, but it will never decrease. Okay, so finally the question is, okay, another thing is the probability of the whole system is, so you assign catalyst amounts to all the n reactions, so you will get probabilities out of this, and the final probability is product of all these n probabilities based on the amount of catalyst you gave to each reaction. And you need to maximize that final probability. Okay, so that is given here. You need to assign C units of catalyst to the n reactions so that the probability of success of this system is maximized. Okay, so this is the final question. So is the question clear overall?
Yes, sir. Clear, sir.
Yeah.
Sir, n reactions, all the reactions have to means they should give the output, no sir?
Yeah, exactly. So each of them needs to run. If any of them has a zero probability, then the overall probability becomes zero.
Okay, sir.
So you need to
But sir,
assign
is
at
it
least.
possible that the solution has zero as some means we want to maximize the total probability? So isn't it possible that one reaction has zero probability, but other reactions have a higher probability so that it is getting maximized?
No, that will not happen because you are doing a product of probabilities, right? So if any of them is zero, your final
Okay, sir.
probability will also be zero. So
I
that
got
is
it.
the
Yes, sir.
minimum
Yes.
case. Yeah. Okay. So right. So now moving on to the inputs. So so the first input is n. So this is telling the number of reactions you have to consider, and 5 is the total amount of catalyst you have available. So this is capital C. And finally, this n cross C matrix, this is the E matrix given. So this first column is saying if you have 1 unit of catalyst applied to any of the reactions, what are the probabilities? So the first reaction with 1 unit of catalyst has 0.1 probability, then 0.1 for second, and 0.2 for the third reaction with 1 unit catalyst. Then the next column is you have 2 unit catalyst or 3 unit and so on. Yeah? So this is the first input, and okay, that is the whole input actually. And then finally the output is something like this. You have to first tell what is the total maximum probability of the whole system. So this is like you find the best solution and give the product of the individual reaction probabilities based on the catalysts you assign. And the second part of the output is saying for each reaction how much catalyst you assign. So as you can understand, the sum of all these assigned catalyst will be equal to C, because that is the total amount of catalyst available. Okay, right. That input output is also clear, right? Okay. So now let's try
Excuse
to
me, sir.
Yeah.
So can you please explain the matrix or matlab? Yes, this matrix input.
Okay. Right. So the matrix given is a n cross C matrix. Okay. So there are n rows. So saying ki this is for reaction 1, this is for reaction 2, up to this is for reaction n. And the rows are saying ki for reaction 1, if you have 1 unit of catalyst, what is the probability? So that is 0.1. If you have 2 units of catalyst, that can be 0.3 and so on. So this is basically a non-decreasing sequence for reaction 1. Then there would be another, again, a sequence for reaction 2. So these are basically saying for any reaction you pick, say ith reaction, you can find if you apply say k amount of catalyst, what would be the probability of that? So that would be your I comma k cell. So clear, right?
Yes, sir.
Okay. So let's
Sir,
try. Yeah.
so in this one we have to maximize the probability keeping the sum of the C constant. That is the constraint, the C.
Yeah. So there are two constants basically. So you need to run all the reactions. So at least you need to assign 1 unit of catalyst, and the total amount of catalyst must be C. So this is the constraint.
I mean, must be C or less than equal to, right?
No, it must be C. You need to utilize all the catalyst available, because you will utilize, right? Because if you throw away some catalyst, your probability will probably decrease.
Right.
Or, yeah.
Yes. Right. Okay.
So yeah, let's try to formulate the solution. So let's assume that we are storing the solution in a matrix DP. Okay, so this is a 2D matrix of size n cross C plus 1. Now why C plus 1? Because we can have 0 units of catalyst or 1 or up to n, right? So we need entries for all of this. So that's why we need C plus 1 columns. Okay, and the DP cells will tell. So DP ij is telling if you consider up to reaction I and you utilize j units of catalyst, what is the maximum probability of the system that you can achieve with that? Okay, so this is up to reaction I, and max catalyst use or catalysts use is j. Okay, so this is basically this particular problem. Now if you so we can write a recursive formulation for this ki dp ij is equals to, so what would this be? So you have a max. Now your final reaction is I, right? So for ith reaction, you can assign some amount of catalyst. So let's call that Z, right? So now if you vary that amount, how much you can vary that amount, you have up to J catalyst, right? And you have I reaction. So first of all, to make the probabilities positive, you need to take away I amount of catalyst from that. Okay, so assigning 1 to each of these reactions. So remaining catalysts are J minus I. Okay, so you can vary the amount of catalyst that you assign to the ith reaction is basically from 1 to, so 1 is basically your minimum amount. So it can, so Z can be 1 to J minus I. Right, so this is the, okay, actually J minus, the extra catalyst. Achha, let's call this the extra catalyst. So basically we have already assigned the 1 unit of catalyst to all reactions. So remaining are J minus I, right? So for reaction I, extra amount of catalyst that you can assign is between 0 to J minus 1, right? So all these sub problems that we will see will basically vary this Z from 0 to J minus I, right? So if we take, say, Z equal to 0, so that will be dp I minus 1 comma J minus 0. Okay, so we basically assigned no extra amount to the ith reaction. Then this will be multiplied by E I comma 1. Okay, so we basically gave the minimum amount, which is 1, to the ith reaction and multiplied that with the previous best solution dp I minus 1 J minus 0, right? So this is for Z equals 0, no extra amount assigned to reaction J. Now the next case will be dp I minus 1
Sir,
J minus, yeah.
Could you again tell what was Z?
Yeah. 1 second. So okay, so Z is basically saying, so we are trying to solve for dp I comma J, right? So here dp I comma J is saying ki we take the up to ith reaction, so 1 2 3 4 up to I, and we take J amount of catalyst, not C, but J amount of catalyst, where J is something less than equal C. So in this case, for the ith reaction, the final reaction, how much extra catalyst that we can take? So that is the variable Z. So what can be the value of Z? So assume that you have assigned the 1 unit of catalyst to all of the reactions from 1 through I. That is the first task to do, because otherwise your probability would be 0. So once you do that, you have J minus 1, J minus I amount of catalyst left, right? Because you assigned 1 to each. So
Sir?
Since this is the max amount, how much you can give to the final reaction, that is between 0 and J minus I, right? Because that is the excess amount.
Sir?
Yeah.
Hello, sir. Sir, J means if we assign all the catalysts here, so there would be no, sir, I means the total amount of extra is J.
No. So J is your maximum total amount of catalyst that you are considering, but J minus I is the excess.
Sir, so if we suppose I am having 1, 2, 3 means 5 catalysts in the last example itself, sir, and I am assigning 2 to 1 and 3 to the second one. So the next one would be 0, sir. So how we are going means how we will remove that case, sir? Like we can't assign all the values of catalyst to this.
We'll get to that point. So here you only consider the reactions up to I. Okay.
Yes, sir. So my point is we have to assign 1 to each, means एक एक सारे n को देना ही पड़ेगा, तो सर तो उसके बाद जो एक्स्ट्रा बचा वो हमको असाइन करना पड़ेगा ना सर?
Right, exactly. So that's what you're doing, right? So we have give 1 to each of the i's. So that takes away I amount of catalyst. So how much is remaining? J minus I.
सर नहीं, ये हम पहले वाले i को दे रहे हैं, हमें सारे n को एक तो देना ही पड़ेगा.
No, so that's what I'm saying. Don't think about the reactions that come later. Only think about these first I reactions for now.
Okay.
Okay. Right. So because we are ignoring those at the moment and we are just trying to solve what would be dp I comma j. Okay.
So the ith reaction taking only J amount of catalyst.
No, not J. So this is okay. So dpij says ki we are taking the reactions up to I. So 1 to 3 through I reactions, and we are taking J amount of catalyst. So all the first I reactions are here.
So that J is less than C. I mean, like only I'm considering just I reactions with only a part of the catalyst, that is J.
Exactly. So J is less than equal C, because as we increase the number of reactions, so we will eventually reach up to C. So that's why J less than equal C. Okay.
And all J need not to be used. Right, sir?
No. So
Yes,
in
sir.
this solution, all catalysts that you have available needs to be used.
Sir, when we are writing dp of I minus 1, j minus 0, that means we have considered the maximum probability which we get if we consider I minus 1 reactions and j amount of catalyst. So, sir, the ith reaction will have no catalyst, sir, because we have already utilized the j units of catalyst in I minus 1 reactions.
Right. Yeah, that is correct. This should be J minus 1. Yeah.
Yes.
Because we at least need one there. So yeah, so now basically we are saying that as we vary J between Z, as we vary Z between 0 and J minus 1, as extra amount of catalyst given to the final reaction, right? So that is basically this E term coming in, and that will be multiplied with the best solution from the previous reactions, right? So because we are taking away the how much catalyst we gave to the final reaction, so the remaining solution is dp I minus 1, j minus 1 for the previous reactions, and only one amount of catalyst given to E, the ith reaction. So that is the probability is E I comma 1. So similarly, we can increase the amount of extra catalyst to 1. So the total catalyst given to ith reaction becomes 2. In that case, the solution reused is dp I minus 1, j minus 2 into the final probability, right? So we can vary this. So this is basically varying z equal to 0, then z equals 1. We have to vary up to z equals j minus I. Okay, so this will, the finally it will be something like I minus 1, and it will be j minus 1 minus 1, right? So that will something be like 2 or something.
I minus 1.
All right, yeah, sorry, I minus 1. Yeah. Correct. Yeah, it will be the equal
Yes,
sign,
sir.
which will be our base case basically.
Yes, sir.
So, and this will be, we give j minus I plus 1 amount to the ith reaction, right? So it will be max of all these cases where you are varying the amount of extra catalyst that you give to the final reaction. Now, how do we show that this has the optimal substructure property? Yeah.
Sir, total amount of catalyst is J, or catalyst use up means is up to J?
No, so for this particular cell that we are filling, dp I comma j,
Yes.
only here
Yes.
the catalyst we are using is J.
Up to J.
Number
Okay,
less
sir.
than
Okay,
equals
sir.
C.
Okay. Yes, sir. Got it, sir.
Okay. Yeah. Okay. So finally, so this part is basically the recursion form. Now we need to see whether the optimal substructure property holds here, right? So how can you see that? We basically wrote down this key dp I comma j in terms of max of some other terms which are based on dp I minus 1 and something, right? Now we are considering ki, okay, so let's suppose ki there is a best solution, optimal solution d I comma j, which is based on some z star, right? So for this we'll have the second term as e I comma z star, and this term will be there t I minus 1, and whatever the remaining amount of catalyst left for the previous reactions, right, based on this extra given z star. So if this solution is optimal, and let's say we assume that this particular internal solution, which is the solution to the sub problem, is not optimal. Now, if this part is not optimal, we can replace this with some other solution d star I minus 1, comma the remaining amount. right? So that will give us the best solution. But if that gives us the best solution, it will increase the probability obtained through that also. So then this Dij will also increase. So since we already assumed that this is optimal, already optimal, so this cannot be suboptimal, Di minus 1 solution. Okay. So basically by contradiction, we can tell that if this is optimal, in this particular formulation, Di minus 1 and the rest of the amount will also have to be optimal. So that's why we can, now we have both the point, we have the sub problem thing, we are able to break down this down to similar problems, smaller problems, and we have the optimal substructure, right? And once you see like what are the calls made in this recursion, so basically if you are trying to solve this I comma j cell, you are basically looking at cells that comes in the previous row somewhere, right? And again, if you try to solve this particular point, this will also try to look at these cells. You have the sub problems overlapping in the formulation also. So both the conditions hold, that overlapping sub problem and optimal substructure. So we can apply a DP based solution. Okay. So this was the formulation. So I will switch a screen to show you the code. Now, if you have any questions here, you can ask, or I will go to the code.
Sir, we can have a base case as dp of ij is equal to 0 if I is less than, if I is greater than j, because
Yeah, exactly. So if the catalyst amount is less than your reaction ID, then it's 0. And if it is exactly equal, then the probability is basically product of all the input probabilities. Okay, so I'll switch to the other screen. Can you see the screen?
Yes, sir.
Okay. So, right. Yeah, the code. So now that you understand the algorithm, basically the code would be pretty simple. So first you take as input N and C, which are given. So taking N and C. Then the E matrix is given. So you basically fill in those cells. So we initialize the E matrix, create the E matrix, and then read the E matrix. So we have all the inputs read here. And after that, we just verify by printing. So this is not part of the output. I was just checking. And so the solution starts here. So in this part, what you're doing, we first create two matrices. One is DP. Okay, so this is the matrix that we saw, which is created using the DP formulation. But we need another matrix called comp to get the actual solution. Okay, so this is generally the case for any DP problem. So we will solve the DP problem using your formulation, and that will give you some number like the shortest path or the best case count or something like that. But to find the actual solution that constructs that minimum value, you will need to use another matrix which will like use some sort of notation to get this solution. Okay, so in this case, so DP is the best case probability. DP will contain the best case probability, but this comp will contain basically comp ij will be what is the amount of reaction, what is the amount of catalyst used for reaction J for that solution in DPIJ. Okay, so DPIJ is the best case solution up to reaction I and using catalyst J, right? So comp ij is basically saying in that case, for that solution, what is the catalyst used by reaction I if the maximum amount available was J. Okay, so this is what is stored in comp. Now, once we have that, we first initialize the matrices. So like one of you mentioned, so DP, if the amount of catalyst available is 0, that will definitely be 0. And even if the amount of catalyst C is less than the reaction ID R, even then the probability would be 0, because you will not be able to assign 1 to each of the reactions, right? Now, once you have, so if that is not the case, so these 0 cases are cancelled out. We have already taken care of that. So if you now have a reaction ID greater than 1, so this is a special case where the ID is starting from 2. So in those cases, you will multiply the previous diagonal entry kind of. So you are basically increasing one reaction and also increasing the catalyst amount by 1. So that is from R minus 1 to R, catalyst amount increased, and reaction ID R minus 2 to R minus 1. So R is actually varied from 1. So that's why we are taking the reaction ID is R minus 1. And you multiply that by the first probability of that new reaction that we are adding. Okay. So this is basically product of the first column in the E matrix. So this is for R greater than 1. And for R equals 1, so R equals 1 is the first row where you have only one reaction.
Sir, shouldn't it be E matrix R minus 1 and 1 because we are using 1 unit of catalyst for that?
Sorry, can you go again?
Sir, where it is written just enough catalyst case, there we will write E matrix and R minus 1 and 1 because we are using 1 unit of catalyst for the.
Right. So the convention is just a little bit different. So we rate the E matrix as size n cross C. So the 0th column is actually when you have one amount of catalyst available.
Okay, sir.
So that's why we are. So yeah, this will be a bit tricky. We just need to keep these things in mind, which IDs and amounts you are using. Okay, so the final.
Again, what is comp matrix?
Yeah, so the DP matrix basically is telling you DPIJ is if you consider reactions up to I and ignore the other reactions and you have J amount of catalyst, what is the maximum probability you can achieve? So that is DPIJ. And comp IJ is basically telling in that case, when you have DPIJ, what is the amount of catalyst given to the final reaction I? Okay, so that is comp IJ.
Sorry, I didn't get. What is the?
Okay. So DP is giving you the best case solution for a certain I comma j case, right? That part you got?
Yes, sir.
Yeah. So now DPIJ, in the case of DPIJ, what is the amount of catalyst given to that last reaction, which is I, right? So that will be some amount out of J which is given to the ith reaction, and that is being stored in compi. Now, why we are storing this? So if you know, so once you have constructed this full matrix, so you will have DP n comma c. So that is the final answer, right? Final maximum probability. Now, if you look at comp n comma c, that will tell you for n comma c how much, and the best case of n comma c, how much catalyst you give to that nth reaction. So that is your first answer to that question. Now, once you get that, you can take away the problem. So you remove the nth reaction and you remove z amount of catalyst, whichever you found in comp n comma c, and you get a sub problem. So then you can look up that cell again after removing that reaction and that amount of catalyst again in the comp matrix. So that will be some other cell which will tell you what is the amount of catalyst given to the penultimate reaction. So this way you can keep removing catalyst and reaction and get to the final solution. Okay. So that is the use of comp matrix. So, okay. So we saw the the first three initialization. Now the last one is that if you have only one reaction. So if you have only one reaction and you increase the amount of catalyst from 1 to C plus 1, then the amount of catalyst, the full amount of catalyst will be given to the first reaction only because you have only one reaction, right? And the probability will be directly the entries from the E matrix, which is basically saying the first reactions probability with C amount of catalyst, C minus 1 being the index. Okay, so this will directly be the first row entry. So this is the first row, and these kind of fills up the diagonal, some kind of diagonal. Okay, so this whole thing is your initialization. So you need to, so that's why I was saying ki initializing in DP is also very important. You need to identify these cases correctly and fill them in first. Only then you can go to the actual recursive formulation which uses the DP thing. Okay, so now this is basically the DP solution. So we are starting from R equals 2 because we know the solution for one reaction. So we are starting from two reactions and going up to all the reactions. And we are also increasing the amount of catalyst available from R plus 1 because with R amount of catalyst, we already know the solution. It will be product of the initial probabilities. It's the base case. So you start from R plus 1, which tells like we have one extra catalyst amount, and we go up till C. So this is the first outer loop. And we also need to get the max, right? So the max is over how much extra catalyst is given to the last reaction that we are considering. So that is this loop for Z. Okay, and within this Z, what we are tracking is, so within this Z, we are seeing, so DP R minus 2 C minus Z. So C minus Z is the amount of catalyst left out after you take out some extra amount for Z, right? And DP R minus 2 is like the previous row. And since you took out Z extra amount of catalyst, you are getting that from E matrix R minus 1, Z minus 1. Okay. And since you are concerned about that case key, there will be some entries when we may take out too much, catalyst from the equation. So in that case, we have already filled the D matrix with zeros. So those all are already made COT, we have zeros there. So any positive value that we get in the D matrix will be valid for the given query. Okay, so this is the individual entries within the max set that we saw earlier in the formulation. And finally, we are tracking which is the max value. So when you have run this whole thing, your max value of DP for that particular DP IJ cell will be stored in S max. And Z max is basically saying for which particular Z allocation to the final reaction, we got this maximum probability. And this Z will go to the COM matrix. Okay. So S max is going to DP, and Z max is basically saying for what extra amount of catalyst assigned to the last reaction, we got the best solution. So this is COM matrix. Now, once you run this loop, your whole matrix is filled. You can just then print the output. Okay.
Sir, in the recursive formulation, we took that if we consider till I and the ith one is optimal, then the I minus 1 is also optimal.
Right.
So if we consider the first reaction itself, if we give the whole catalyst to it, then it will be the optimal for that.
No, it will be optimal for just that, but the rest of the probabilities will get 0, right? So the overall solution will not be optimal.
But sir, we are considering only till ith at the IJ.
No. So you have to think about the whole formulation. So when you are looking at DP I minus 1, so that will consider the other probabilities, because that will again break down recursively, right? So it's not easy to think about this like optimal solution simply because there is a recursive formulation. So the first one is optimal only when the second internal DP I minus 1 thing is optimal. Now DP I minus 1 is optimal when its recursive formulation is optimal, right? So since this constraint is there, it will never be 0 because that will not be optimal, right? And so you are worried about the case key if DP I minus 1 we assign all the amount to that, it might get the best solution. So it will not get, because all the cells that are caused by that kind of scenario, if you are assigning too much catalyst to one of the cells, so that will already be 0. Okay, so you
Sir, when we multiply the value in the E matrix, that value is becoming 0. So it is automatically cancelling out because we multiply with E matrix and then we see the value of the particular solution, whether it is optimal or not.
Yeah.
So we are considering the extra catalyst to be added till the ith one, right? So the J minus, all the remaining J minus I catalyst units, if we are adding to the final one, then we will get the Eij position, like E I comma J minus I plus 1, right? So for that instant, it will be the maximum.
No, sorry, I didn't get the question. Can you go ahead?
Sir, in the PDF, you wrote that we will consider the max of A. So can you open that PDF?
Yeah. Yeah.
Here, yes, sir. Here the DP I minus 1 E I comma J minus I plus 1, the last term.
Yeah.
It will be the maximum, right?
No, it may not be the maximum, right? So that's why you are pairing Z and finding the maximum.
Yes, sir, because it would depend on the previous values also.
Exactly, it will depend on the DP value and the E value. So
yes,
both of the things are.
Yes, sir. Here the second argument will matter. Yes. Like DP I minus 1, then if we take I-1, then it may not be the maximum. If we take some other, it will be maximum.
Exactly. So since this is product, we cannot directly say which one will be maximum. Both of them are varying, right? So both the values are different.
Okay, sir. Yes, sir, it is.
Okay. So okay, then I will share the tutorial PDF and also the solution code, so you can look at it. Okay.
Thank you, sir.
Yeah.
Okay, so I think like we can close here. Maybe like Bishal, you can share the codes with them, but I would request you guys to also try writing the code yourself. Okay, try some of the codes that we are sharing with you. Try to write if you have time. Try to. I know you have time crunch. If you have time, like try to write some of the code yourself. That will give you more, a solid command. And also try to see the examples on GFG. So I guess all of you know what is GFG. So like try to see like all the DP problems under GFG and like see
And
the
sir,
solution. Huh?
sir, like
Hello?
last time, Pawan sir did, can you please share some questions where we can submit our solutions and we can check all our solutions?
So that you can do also on HackerRank, right?
Yes, sir. Means last time,
So,
sir shared some links.
Yeah,
okay.
for that practice, actually, you can look into either GFG or LeetCode. So they have like well categorized set of problems.
Yeah,
So you
I
can
think
just
in
look into,
GFG you can
yeah.
also submit your solutions and check.
Yeah.
But I can always share. Like if you see GFG, I mean, if you type this, I think.
So it's there in HackerRank too.
Yeah, it's there in HackerRank too.
The algorithm, then dynamic programming, the problem solving part.
There will be a bunch of problem where you can do it and solve it and submit. So just type with this keyword, you will get.
Okay, sir.
I will also
Thank
try
you,
to
sir.
find out a few things and send you.
Sir, what we want is in a well organized, like in the last week when we practiced from easier to harder, then we got some idea how to proceed. That's what we want actually.
Okay. I'll try to see like if we can get something similar and send it to you.
Yes, sir. Thank you.
Okay.
So stop recording, please.
Yes, sir. Sir?
Sir, go on.
Vishal, sir.
Vishal, sir. Hello, Vishal, sir.
Everyone just leave now. हो जाएगा बंद recording.
Okay, sir.